60 years ago, scientists at Los Alamos developed nuclear propulsion engines built for the stars. Their creations worked, proving the concept of deep space nuclear travel. But fate intervened. Programs were canceled, funding vanished, and for 6 decades, humanity remained imprisoned within the inner solar system, reliant on solar energy and radioisotope generators confined by their own limitations. Near Earth, the sun provides abundant power. Missions like NASA's Psyche thrive on solar electric propulsion, efficiently using ion engines. But beyond the asteroid belt, sunlight dwindles. Past Jupiter, Saturn, and onward, spacecraft dim, their solar panels reduced to useless weight. Every deep space mission strikes this persistent wall. Plutonium-fueled radioisotope thermoelectric generators, REGs, have powered legendary probes like Voyager, Cassini, and New Horizons. Yet REGs are tiny power sources. They're expensive, rare, and can't scale to the megawatt ambitions of future interplanetary travel. NASA's Krusty reactor carved a path for lunar energy, but transforming nuclear heat into vibration-free electricity remains unresolved. Enter Kepler's orbital Stirling technology, a leap for lunar bases. Yet for propulsion, the answer must be more radical: solid-state generation with no moving parts. The revolution begins with a chip. At the AWALM 17 workshop in Bergamo, Italy, physicist Fabrice David unveils 2 pivotal papers. The first introduces a modified silicon wafer, akin to those in your phone, bombarded with palladium atoms to form millions of microscopic junctions, each infused with hydrogen isotopes. Suddenly, these junctions produce electricity, a steady current, absent batteries, chemical reaction, or fuel. This process is propelled by the Entman-Gordon effect, named after research teams who saw particle emissions from fusion diodes and sustained electrical outputs from lattice energy converters. The phenomenon is stubbornly reliable, its physics still not fully understood. David's key evidence lies in negative differential resistance. Conventional junctions increase current as voltage rises. David's, counterintuitively, drop current with rising voltage, a signature of active, nonlinear energy injection. Scaling up, semiconductor fabrication allows 1 billion junctions per wafer. 10 nanoamps per junction becomes 10 amps per wafer, stacking to 100 watts, enough to challenge REGs on cost, safety, and longevity. This isn't just a battery replacement. David presents the Kepler engine, a hybrid propulsion system with 2 distinct modes. Mode 1 employs the microwave electrothermal thruster, MET, pioneered by plasma physicist Dr. John Brandenburg. Electricity from the energy chip powers microwave emitters, which heat propellant gases like water vapor, found on asteroids and lunar ice, to extreme temperatures, producing thrust. Mode 1 offers deep space independence, refuelable from local resources, without need for solar proximity. Mode 2 defies traditional limits. David and Brandenburg propose using nuclear reaction products directly as exhaust. Fusion in the chip produces fast neutrons with velocities unimaginable by any chemical rocket. Yet, LNR reactions in palladium don't yield neutrons until Professor Konrad Czerski's discovery, the Czerski-Vallet effect, where fusion releases energy as electron-positron pairs rather than gamma rays or neutrons. To create neutrons, another effect, the Parkhomov-Belousov effect, induces inverse beta decay in metals, generating neutrons at 8% the speed of light. These combined effects give the Kepler engine its power.